Hi, today we're going to go over the fluid mechanics behind a chainsaw engine. Now, for context, we took apart a two-stroke engine and identified three major components: the carburetor, the rotor, and the piston assembly. Here's Reggie to talk more about the carburetor.
One of the most important fluid mechanical devices to the operation of any engine is the carburetor, as it allows the cylinder to breathe in fuel and air in an appropriate mixture to promote efficient combustion. It does this without the aid of any technology or any sensors, meaning it's powered strictly through the principles of fluid mechanics. As you can see, the carburetor has a couple of different components, but the key geometry that motivates the function of the carburetor is the venturi, which is a pipe with a restricted cross-sectional area here at the throat. As air passes through the throat through conservation of mass, we know that this restricted area leads to an increase in air velocity. Through Bernoulli's equation, we know that increase in speed leads to a decrease in local static pressure. Carburetor takes advantage of this by injecting fuel at this low pressure region, since there's a vacuum there that literally sucks in the fuel in order to be mixed with the air and pass through the cylinder. Since we know that Bernoulli's equation is the underpinning principle for the function of the carburetor, we must prove that it is an appropriate model in this instance, i.e., we must prove that flow through the carburetor is inviscid and incompressible. Using measurements we found through our dissection and approximated values from other chainsaws, we're able to find the Mach number through our carburetor was less than 0.3, and it had a Reynolds number of 23,000, which is well above the 10,000 range, meaning viscid effects can be ignored, and the flow is in fact inviscid and incompressible. Now that we know that Bernoulli's equation is applicable, we can calculate the pressure drop across the carburetor and see exactly how hard the engine is sucking in fuel and air. And we can also calculate the mass flow rate of the air and fuel respectively and see which creates an upper limit for the horsepower and torque that the engine can generate. So also calculate the air fuel ratio, which gives us a key insight to the optimality and the optimality of the fuel and the engine performance. For example, we calculated our air fuel ratio through our carburetor to be 6-to-1, which is very lean in respect to what it should be in real life, likely due to inaccurate measurements or inaccurate simplifying assumptions. However, it shows exactly how the carburetor impacts engine performance and overall chainsaw performance.
Introducing the cylinder and piston assembly, I've highlighted some important parts. In the red, the intake pipe from the carburetor shaft is circled, while in blue you can see the exhaust pipe, which leads into the exhaust tank and then out to atmosphere. The ports circled in green are where intake and exhaust gases during the piston cycles are able to move down into the crankcase, where using the oil mixed into the gasoline, it helps lubricate both the crankshaft and the piston cylinder walls for efficient operation. The piston on the right looks as you might expect, with the main cylindrical portion attached to the crankshaft. During the upstroke, the piston's upward movement compresses control volume V2 of fuel air mixture, while it's ignited by the spark plug at the top, which discontinuously increases the static pressure, volumetric kinetic energy, and in turn its stagnation pressure P2 naught. At its peak height, the piston covers both the transfer port and the exhaust pipe. During the downstroke, the high static pressure P2 pushes the piston past the location at which the exhaust pipe is placed, where the fluid of volume V2 rushes in, overcoming fluid to atmospheric pressure. A streamline starting in the upper volume has a Bernoulli constant initially dominated by the static pressure and kinetic energy terms, but turning mostly to static pressure as it gets farther from the exhaust tank. The piston then hits its lowest point, uncovering the transfer port while pushing some V1 fluid down into the crankcase, and the rest out through the transfer ports and now above the piston. The upstroke combustion products are now being replaced by the fuel air mixture filling into the cylinder, completing the cycle.
The flywheel is mounted directly on the crankshaft, so it rotates in sync with the piston's motion. Along the rim of the flywheel, there's a magnet. Each time that magnet passes the stationary ignition coil, the changing magnetic flux induces a voltage and fires the spark plug. The flywheel blades operate like a centrifugal impeller. If you look at the flow through the blades, the mass flow rate remains constant as the air moves outward. Because the flow area increases with radius, the radial velocity decreases roughly as 1/r. At the same time, the rotating blades impart a tangential component to the flow. Since the blade speed increases with radius, the azimuthal velocity grows in proportion to r. When you combine a decreasing radial component with an increasing tangential component, the total fluid speed increases as the air moves outward. The extra kinetic energy and the associated rise in pressure comes from the work the engine puts into spinning the flywheel. All of this produces the outward cooling airflow that moves across the cylinder fins and the ignition components, carrying heat away from the engine.
From our measurements, the flywheel has an outer diameter of 121 millimeters, a 54 millimeter hub, and about 33 millimeters of blade height, which gives an outlet flow area of roughly 9 times 10 to the negative third square meters. And under normal cutting load, the engine runs close to about 8,000 RPM. That gives a rotor tip speed about 50 meters per second and a Reynolds number around 10 to the fifth, meaning the flow over the blades is fully turbulent. To estimate airflow, I use a standard radial fan assumption that the average exit velocity is around 40% of the tip speed, so roughly 20 meters per second, which gives a flow rate about 0.19 cubic meters per second and has a mass flow rate around 0.22 kilograms per second. Using Bernoulli's dynamic pressure, that velocity corresponds to a pressure rise of about 250 pascals, which translates to a fan power about roughly 50 watts, which is small compared to engine power but enough to cool the cylinder effectively.